All right, let's get this show on the road. Hello, everyone. Welcome and thank you for joining us today. My team and I are excited to present Embrasure. Embrasure is an open source, self-hosted secrets management tool for small teams seeking simplicity and security. But before we get into what all of that means, let's start off with our agenda for the day. Our presentation will consist of two sections. In the problem domain section, we'll talk about understanding secrets and common ways secrets are exposed. We'll also discuss what challenges are involved with securing secrets in a dev team before introducing secrets managers and considering the trade-offs of using a self-hosted versus managed solution. In the second section, we'll introduce Embrasure, taking a tour of its core design principles before finally taking a deep dive into the architecture of Embrasure. Then to wrap things up, we'll hold a Q&A. My teammate Taron will take it from here to get into the problem domain.
Thank you, Chase. Before diving into secrets managers, let's first explore the concept of secrets by answering some fundamental questions. Let's start with a basic question. What exactly is a secret? According to IBM Cloud, a secret is any piece of sensitive information. A more software-centric definition, though, would be that secrets are private pieces of data that unlock protected resources or sensitive information, such as third-party APIs or databases. Now that we have a clear understanding of what secrets are, let's explore why they are necessary and what problems they help to solve. Secrets protect sensitive information from unauthorized access. By utilizing secrets, developers can confidently ensure the integrity of their system and protect it from potential security breaches and malicious attacks. This not only enhances system security, but also ensures that sensitive data can only be accessed by authorized users, thus strengthening the system's protective layers. We've established what secrets are and why they are used. But expectedly, there are some trade-offs that come with using secrets. Mainly, the secrets can be a weak point in a project's security. They are an Achilles heel that, if discovered, can be exploited to gain unauthorized access to a system or to steal user information. Therefore, the most significant challenge of having secrets is keeping them protected and preventing them from being revealed. With that, let's examine some common ways that secrets can be exposed. Secrets can be vulnerable to exposure in two stages: at rest and in transit. At-rest exposure happens when secrets are saved or stored in a dormant state, like in a database or code repository. In-transit exposure, on the other hand, occurs during communication over a network. In-transit exposure is a serious threat whenever plain text or unencrypted information is transmitted over the internet. However, it can be significantly mitigated by utilizing secure HTTP, better known as HTTPS, which encrypts information during transmission. One of the most common instances of at-rest secret exposure occurs when secrets are hard-coded into a code base. It's likely that everyone listening has, at some early point in their engineering career, hard-coded an API token or database password, even though we were aware it wasn't a recommended practice. The danger of hard-coding secrets is the possibility of uploading them to a public repository and thus making them available to unauthorized individuals. This situation is commonly known as secret leakage. The prevalence of secret leakage is extensively documented. In 2019, North Carolina State University researchers scanned almost 13% of GitHub's public repositories. They found that not only is secret leakage pervasive, affecting over 100,000 repositories, but thousands of new unique secrets are leaked daily. These stats confirm that secret leakage is not an isolated occurrence, nor is it limited to new developers. It is a widespread concern that all development projects need to remain vigilant about. As we discussed earlier, using secrets in a responsible manner poses certain challenges. These challenges become even more complex when the secrets are shared amongst multiple developers in a team. As a team grows in size or experiences turnover, it becomes increasingly challenging to keep track of who should have access to what information. This is a widespread occurrence in software projects and is often referred to as secret sprawl. Secret sprawl is the uncontrolled spread of confidential information. This can occur in various forms, such as passwords shared in email chains, multiple personal Slack chats, or even passwords being passed around on sticky notes. Every instance of secret sprawl poses a unique security risk, and as previously mentioned, the potential for a security breach carries significant financial and reputational costs. It is then crucial to find a more secure alternative. From these challenges, a solution emerged. Secrets managers. In order to address these challenges, tools for securely storing and accessing sensitive information were created. These tools, known as secrets managers, provide solutions to problems such as controlling secret sprawl, synchronizing secrets for the entire team, protecting sensitive information, and securely distributing confidential data. In essence, secrets managers are software tools that securely store, manage, and distribute sensitive information. Let's explore how secrets managers typically deal with these concerns. Sharing secrets amongst a group of developers can pose significant challenges. What happens when someone on your team changes a secret? The dynamic nature of software development teams can quickly lead to secret sprawl if left unchecked. So, how can you ensure that every team member has access to the updated secret? The answer is centralization. Having a single source of truth solves two of the challenges of having secrets: pushing updates to all teammates and reducing the number of places where secrets are kept. It is natural to have concerns when you learn that secrets managers store all of their sensitive information in one central place. The worst case scenario would be if an unauthorized individual gains access to this location, which would result in a catastrophic breach of security. To protect against this single point of failure, centralized secrets must be protected from unwanted access. This can be achieved through various methods, such as encrypting all stored secrets and limiting access to a select group of authorized users while controlling their level of access. So we just said we can solve protecting secrets by controlling who accesses them, but that raises a whole new problem. How can you confirm a user is who they say they are? All secrets managers must provide some means of authentication to identify users and confirm they are actually that person before allowing access to the resources they request. The most recognizable form of credentials is, of course, a username and password. Authentication alone is not enough, though, to secure access to secrets. What if a user's authentication credentials get leaked or are compromised in some way? No secure organization gives everyone access to every single sensitive document. Each developer's access to secrets increases the risk of secret exposure. So secret managers allow teams to specify what secrets individual developers do or do not need access to. From here, my teammate Ivan will continue our exploration of secret management tools.
Thanks, Taron. So far, we've covered the importance of secure storage, but we now have a problem. How do we transfer these sensitive secrets to where they're needed within a software application? What does this transfer process entail? And how can we prevent unauthorized interception during transmission and make the transfer process as seamless and effortless as possible? The solution to this problem is called secret injection, which can be implemented through several standard methods. The three primary implementations for secret injection are HTTP API calls, SDK commands, and program wrappers. Some secrets managers expose their service through an API. So in this implementation, secrets are fetched by sending requests to various API endpoints. Under the hood, the API fulfills the request by communicating with the database and sends back a response. Another common strategy is to provide an SDK with easier to use function invocations. A well-designed SDK can abstract away complexities associated with working with an API directly, but migrating to an SDK-based secrets manager can require significant rewrites to an app source code and result in vendor lock-in. The third option for secret injection is using a program wrapper, or wrapper for short. A wrapper is a secure gateway that retrieves and injects secrets into your application at runtime. In other words, wrappers preload secrets before your application runs and then initiates the application as a child process with the secrets injected as environment variables. This allows your application to access secrets both safely and without direct modifications to the source code. Many secrets managers also track how stored secrets are accessed through an audit log. Audit logs provide a comprehensive record of events such as accessing, modifying, creating, and deleting secrets. Not only do they give organizations a clear overview of the characteristics and timing of interactions with secrets, but in the case of a potential security breach, audit logs enable quick detection and response. Like many other tools, secrets managers can typically be deployed in two ways: self-hosted and managed. Self-hosting involves deploying the secrets manager within the organization's infrastructure, while managed solutions outsource the management of secrets to a third-party provider. In the age of cloud service providers, self-hosting is no longer synonymous with owning your own hardware, but can instead mean relying on a cloud provider to host infrastructure you otherwise control. When secrets managers offer a self-hosting solution, users install the secrets manager instance on their environment. The main advantages of this are that users have direct control over their data and their infrastructure. However, that also means that they are responsible for maintenance and other administrative management duties. On the other hand, cloud-based managed solutions are services provided by third-party vendors that allow users to offload their maintenance, security, and management responsibilities to the vendor. This option is usually more convenient as users don't need to worry about managing their own architecture. However, managed solutions do not offer the same level of control as self-hosted solutions and tend to be more costly when compared to self-hosted solutions. Now that we have context on secrets and the world of secrets management solutions, the stage is finally set to introduce Embrasure. Embrasure is a self-hosted secrets manager for small teams prioritizing simplicity, security, and record keeping. From the start, there have been 5 core principles that guided the design and growth of Embrasure. These core principles are: 1, creating a user-friendly and easy-to-understand interface. 2, keeping administrative control and ownership firmly in the hands of the users of Embrasure. 3, maintaining a reliable, highly available, and highly secure secrets manager. 4, implementing a solid means of authentication and authorization for all Embrasure actions. And 5, providing a means of monitoring and recording all user actions with Embrasure. So let's go a little deeper into how these principles influence the building of Embrasure. So the first principle, user-friendly design, we designed Embrasure to be developer-friendly and accessible to users users with varying technical backgrounds. To achieve this, our CLI has intuitive commands and a simple setup which automates the process of building everything a user needs to manage their secrets through 2 CLI startup commands. Embrasure has standard CRUD operations for interacting with secrets and creating authorized users. In the image, we are using the add secret command to add a secret to the database. In this example, we are adding a secret with the name maps_API that has a value of the API key. The second principle, administrative control and ownership, Embrasure is fully open source and self-hosted. This ensures administrators have complete control and ownership of their secrets management instance and visibility of its entire architecture. By making the entire codebase accessible, administrators can deeply understand the system's inner workings. This transparency also allows for comprehensive audits of Embrasure's security measures to help foster trust within the user community. The third principle, security and availability, there will always be another adjustment or tool that organizations can implement to increase security, but each addition makes that system more and more complicated to understand or operate. We debated and considered many alternatives and features to balance security, simplicity, and usability during the design of Embrasure. We built Embrasure to minimize the attack surface area while providing high-level security and reliable access to your secrets by leveraging established AWS standards for end-to-end encryption and dynamic scaling. When possible, we also leverage trusted and battle-tested AWS tools to scale with variable network demand and achieve high availability for users. The fourth principle, authentication and authorization. Each time a user sends a request to Embrasure, a prerequisite process of authentication and authorization is initiated on the request. Authentication is the first step in the process that confirms a user's identity by verifying their credentials. Authorization comes next, determining the resources the user can access and what actions they can perform. If the user is both authenticated and authorized, the server will proceed with the request. Otherwise, it will be rejected. The fifth principle, user action monitoring. Embrasure records all user interactions to provide comprehensive visibility into how secrets are accessed. Audit logs are critical as they provide valuable information and enable effective incident management. They provide observability of events, enabling teams to monitor and review access to the secrets, see unauthorized attempts to access resources, and investigate security incidents. Essentially, audit logs provide a way for teams to see what happened and maintain accountability for an organization. Next, I'll hand it off to my teammate Chase, who will lead covering Embrasure's architecture.
Thanks, Ivan. All right, let's get technical with Embrasure. We will be exploring under the hood by beginning at the simplest iteration of Embrasure's design, then progressively work our way through each incremental increase in security and the corresponding architecture that enables it. Cloud services are currently the industry standard for building highly available software. So let's begin with the enclosing envelope of most cloud-native software, the VPC. The network that separates a cloud project from the rest of the cloud is the virtual private cloud, or VPC for short. The VPC groups resources into logical clusters and controls communication between them and with the outside internet. It enables this by providing a private and optional public IP address for every resource created within the VPC. Industry best practices recommend placing resources that handle private or sensitive data being deployed to the AWS cloud inside of a VPC, which is advice Embrasure strictly adheres to. The VPC acts as the container that houses all of the moving parts that make Embrasure function. Now that we understand where all of Embrasure's resources are stored, we can talk about the heart of its architecture, the database. We required an encrypted database that can store all of Embrasure's secrets. So we implemented a traditional SQL solution using an AWS RDS instance running Postgres. So, taking stock of Embrasure, we now have a highly accessible database in the cloud, but anyone who knows the database's IP address can access it. This lack of security is unacceptable for a secrets manager. So now let's move on to upgrading the network security. During design, we found it quite unsettling that by default, the database was publicly accessible to SSH into if you knew the IP address and had the admin credentials. Given the importance of the database, we felt it was unacceptable that the database could be hijacked if this information was leaked. Because of these concerns, we took measures to privatize the database and the VPC's subnets, which are just logical groupings of IP addresses inside the VPC. What this does in practice is eliminate the database's public IP address, making it unable to receive any communication that originates from outside the VPC. These measures effectively seal off the database and Embrasure's inner workings, ensuring that interactions are limited to specific, secure channels within the controlled environment of the VPC. This strategic approach to database protection aligns with industry best practices. So, what's the current state of Embrasure now? We have an isolated database in the cloud that can only communicate with resources inside the VPC, and all resources in the VPC are private. But we've created a new challenge for ourselves. How does a client outside of the VPC communicate with the isolated database containing all of their information? Our solution to that challenge is to build an API server as a communications middleman within the VPC, using AWS API Gateway and AWS Lambdas. AWS API Gateway is a fully managed service used to create, publish, maintain, monitor, and secure APIs at any scale. It acts as a secure gateway for connecting various applications, enabling seamless communication with other AWS tools. Embrasure uses the API Gateway as the conduit for secure communication via its managed API endpoints. These endpoints, secured by TLS to ensure HTTPS communication, form the bridge through which users interact with Embrasure. It provides a well-organized and standardized approach to API management. Using TLS and HTTPS allow all API calls made by Embrasure to be encrypted in transit, guaranteeing that the sensitive information contained in each request response cycle cannot be intercepted and read in transit. But API Gateway only gets us a controlled entry point into the VPC while directing data to other resources. We still need a tool to process the requests coming through the gateway. We choose to perform that processing with AWS Lambdas. But what is a Lambda? AWS Lambda is a serverless and event-driven compute service. They eliminate the need to manage servers or backend resources, and they dynamically provision resources, allowing for automated scaling based on load process requirements. Now that we understand what a Lambda is, we can discuss the design choices orchestrating Embrasure's API Gateway to receive secure HTTPS requests from the CLI. This setup involves adding custom-generated user identification headers to each request sent to Embrasure's Lambdas. Each Lambda assumes the role of a vigilant listener, empowered with the necessary permissions to authenticate incoming requests with AWS IAM and communicate with the database. Its responsibilities include converting requests into the requisite SQL queries, querying Embrasure's central database, and processing the returned response. The orchestrated workflow ensures that the Lambda effectively serves as an intermediary, connecting the secure CLI command execution to the operations within Embrasure's central database. The user receives the processed response through this Lambda, completing the seamless and secure transaction initiated by the Embrasure CLI command. Our build of Embrasure has become quite fleshed out now. We have an isolated cloud-hosted database that users can access their stored information from utilizing an API server. But there are still core design principles we previously alluded to that remain unfulfilled. Requests made by Embrasure CLI commands are supposed to be authenticated to confirm that the user sending the request is cleared to access whatever they're trying to access. So with that, let's dig into just how Embrasure authenticates users. User authentication is one of the most challenging aspects of security to get right. In Embrasure, authentication is handled by AWS's Identity and Access Management Service. IAM allows us to create, manage, and authenticate users within an AWS account. Each IAM user has a corresponding user account on the database. It is through this database user account that we can manage authorization for the user and what they are permitted to do on that database. When a user runs an Embrasure CLI command, an HTTPS request is sent to the corresponding endpoint on our API gateway connected to our Lambda. This request includes headers that will be used in the user's authentication process and will enable an SSL connection to the database, which is required for IAM authentication. Some of these included headers in the request are the user's IAM username and a generated IAM authentication token. AWS IAM uses the access keys stored in your .aws folder to generate database authentication tokens, eliminating the need to store database user credentials. These access credentials are the basis for generating an IAM authentication token, a distinct string of characters requested and generated by Amazon RDS. Embrasure uses the signed IAM authentication token to verify users, rather than a traditional database username and password. Once the user's request containing their IAM username and IAM authentication token reaches the API server, those credentials are used to connect to the Postgres database. The database checks that the credentials are valid using IAM and that the user has an attached IAM policy that authorizes them to connect to the database. Once connected to the database, privileges defined on the Postgres database authorize what actions the user can perform on the database, such as creating, reading, updating, and deleting secrets. These permissions are applied to the user by the admin using the Embrasure CLI. Once the database query completes, a response is made and sent back to the user's client. There is now one final technical hurdle Embrasure sets out to solve that we have not yet discussed. That is the challenge of keeping a record of every attempt to access the secrets stored by Embrasure. We considered implementing AWS CloudWatch, a potentially costly logging tool provided by AWS, or building an access audit log from scratch. CloudWatch was an attractive option, as it is a built-in tool in the AWS ecosystem, but this came at the cost of increased complexity in our architecture, increased financial cost, and increased required technical knowledge from the administrator, as they would have to be familiar with CloudWatch to be able to access the log. These concerns eventually pushed us to building our own access log tool. Since all traffic to Embrasure goes through a single point of entry, the predefined endpoint on the API server, building the audit log tool was simply adding a middleware to the Lambda that parses the metadata of each request entering Embrasure and adding it as a new entry to an access log table in the database. So now that we've finished our walkthrough of Embrasure's architecture, let's take a minute to see it through the lens of a CLI get secret command issued by a user. The request response cycle begins with a user executing a CLI command. That command is converted to an HTTPS request and sent to AWS API Gateway's managed endpoint. API Gateway then routes the request to an available AWS Lambda within the VPC for processing. The request headers are processed by the Lambda using IAM to verify the user's identity. And then the request is then converted to a SQL query and sent to the database. Upon reaching the database checks the ID of the request to see if they have permission to perform that request. If the user does have permission, the query is performed and the response is returned to the user. Finally, an all-new row in Embrasure's audit log is added from all the metadata of the request. And with that, the request response cycle is completed. Embrasure has been presented to you by my teammates, Taron Avagyan, Ivan Lee, and myself, Chase Sobey. Thank you so much for joining us, and feel free to ask any questions now. So, looks like we have a couple questions to start things out. First one is, what are the IAM policies that are being attached to the new IAM user? Ivan, do you want to take care of that one?
Yeah, sure. So there's basically two major policies that are attached to any new IAM user that's created. The first one allows the IAM user to list out what user groups they are part of. This is kind of involved in like managing users. The other policy is a policy that gives the permission to the IAM user to actually connect to the database. So this is kind of one part of this process of allowing the IAM user to connect and to interact with the database. The other part in the policy is that it also has a the database username that is connected to the IAM user. And so that should show up and correspond with the username in the database, and those should line up to enable the IAM user to connect. Those are kind of the two major policies attached to a newly created IAM user.
Great, awesome. Thanks for answering that, Ivan, and thank you for asking that question. So I see one other question. Could you elaborate more on how a client outside of the VPC can communicate with the isolated database? Yeah, I can talk about that. So all client network requests are routed to a secure URL endpoint that's generated by AWS API Gateway. And that's actually a managed service in the AWS cloud. So it takes care of creating that for us. And from there, API Gateway can actually create a secure tunnel into our VPC to connect to an available Lambda within Embrasure. And from that point, the Lambda is able to establish an SSL connection to the database. Since the Lambda's request is originating from inside the VPC, the database can actually accept this connection request. So from there, it's just all the processing that we talked about earlier. Great. I'm not seeing any additional questions. So thank you so much for coming out and taking a look at this. We really appreciate it.